Hello, my good friends. Hello, my RF and microwave associates. Whether you're practicing designing engineer or a graduate student, I welcome you to my sessions. Uh, Today, I'm going to talk about a concept that was, I've covered about 6 or so videos on waveguide to various form of transmission line transitions, to microstrip, to suspended line, to coplanar, and they're in my videos. You can watch them, by the way, if you like to. But I've got a client that has a special need for a transition that is inline, meaning it does the feed, the coaxial feed or the microstrip line feed is not perpendicular to the direction of the E field propagation or the axis of the waveguide, the feed waveguide. So I went in and researched a little bit and came up with some modified versions of what people have developed along the years. So I have two designs, and I was going to cover them both in one video, and it turned out to be a little difficult to do that. So I would rather cover one first right now. This one that you see here, this is the first one. And what this is, okay, we've got a waveguide, which is on this side here, okay? This waveguide, we need to feed it with a substrate integrated waveguide, which is nothing but a printed circuit board. And you can refer back to my videos. There is a whole video on SIWs, so you can refer back to that video for this purpose. I welcome you to do that if you like that. But anyway, it's basically a BCB that is double-sided, top and bottom, as you can see here, and it's stitched with vias along the sides in here. And this actually, okay, when you feed it via an RF signal on this side, it becomes as a waveguide actually. With the only thing about it is the height is the substrate height, basically. It's a reduced size waveguide, basically, rectangular waveguide, okay? Now, for the TE10 mode, it doesn't really matter how high. It's just a matter of impedances, okay? But for the mode to propagate and the cutoff frequency, it becomes basically irrelevant. The height is not an issue as far as propagation or the mode, okay? Now, why do we use substrate integrated waveguides? Because usually we have this in a transmitter or receiver. We're either getting a feed from here, the signal comes here from an aperture of some sort, a phased array aperture, or a single parabolic dish, or a batch that is fed by a waveguide. And then eventually we have to get that signal into planar form so that we can process it. Meaning for the downlink, it's basically the low noise amplifier and the block down converter and then the digital signal processing section that implements the demodulator. Likewise, also it's usable when you have a transmitter on this side and you want to transmit the signal. This signal here might come from you have a GaN power amplifier, and you might want to have the output gets fed to a parabolic dish or an aperture in here, and you get to the waveguide from the substrate integrated waveguide, SIW here, we have to do some kind of matching because the impedance looking into the waveguide, okay, let me look sideways on this so that we can, okay, just, okay, so, well, this is the SIW. So we come into the SIW and then we have some kind of stepped ridge waveguide. What you see here is that the dark color is basically the air-filled material, the cavity inside the waveguide. So this section from here to here is the standard waveguide in here. And this happens to be in the Ka band, KK band. And then from here to here, we have a stepped height, which basically all it is a Chebyshev transformer with a quarter wavelength each length. And the purpose of this is to match the substrate integrated waveguide, the printed circuit board here, to the TE10 mode here, okay? And in a minute, we're gonna see how that is done. So let's get started. So I forgot to introduce myself. My name is Mohamed Nezami. I'm a independent contractor for RF circuits and microwave circuits and systems. I have plenty of years for designs with various companies back in the US and elsewhere, in Europe and in Asia. I'm back semi-retired in Jordan, and I've just started to cater to clients to design remotely and help them out with designs in North America and Europe. I have a very competitive rate, so I work and adjust my time to coincide with their time. And it has been very well so far, with thanks to technologies post-COVID, you know, all the remote tools and accessibility that I've got enabled me to continue working on what I love doing, okay? So if you have a project or if you have a need for an existing design or a new design, please reach out to me. I'm very competitive. So you can outsource your design for me. I'll design it. I'll turn in the modeling, simulations, the BCB, the schematics, and work with your engineers on that until you get your board. I could occasionally fly in for testing and verifying and critical meetings, CDRs, PDRs, whatever. Okay, I have an incoming training workshop that I'm doing for 3 days. I'm going to be basically presenting and training people on basically what's in my videos. Go to my videos. If you like what you see in there, we're going to sit down, start from the ground up, assuming that you have a Bachelor of Science of Electrical Engineering and all the appropriate communications and RF and microwave courses, E-fields. We're going to sit down and basically walk you through the designs. It's hands-on so that everybody that comes in, prior to that, we would set them up to get their Ansys package. And then, so we would, they would come in and they would have hands-on, we'll have workshops. It's in a real nice hotel here in Roman Jerash in Jordan. And the price is very reasonable and includes the 3 nights at the hotel, plus the meals and so on. So give me a call or email me if you like to come and let me know if you like to register. Okay, so today's session is basically substrate integrated waveguide, okay, to rectangular waveguide transition, okay? So if you're interested in the other sessions I had, and of course it's inline really. I forgot to type that in here. There are some other transitions that are not inline. This one is inline, meaning it's the same axis, so it's very compact and it has a few other benefits as well. So if you like to watch my other 5 videos on the other transitions, you can do that. So this is what we're going to talk about today. It's pretty nice, simple design here. And it's made of 4 parts, basically. We have the standard waveguide, which is here, okay? And then we have a substrate integrated waveguide. it's a printed waveguide, basically. The way it works, you have a stitched via walls in here. They act like sidewalls, okay? And then the width of this, and of course, the height is the height of the substrate, okay? And the spacing between the vias determines the cutoff frequency that you would get. Other than that, it acts exactly like a waveguide. Between the SIW and the standard waveguide, there are sections, and these three sections in here, they're basically chip. So we have the SIW, the substrate table, which is in here, and I'll talk about that in a minute, okay? And so then we have these are the three sections of a Chebyshev transformer, okay? And the first one is loaded with a dielectric, an extension of the dielectric of the substrate, the SIW. We strip the copper from this one, and we have a little taper that basically takes the signal, as you can see here. This is basically the taper section. It's an extension of the substrate. So it goes in like this. And the reason to do this is because we need to make a gradual transition for the E field so that we don't get reflections. And there is more to it that is beyond the scope of this sessions right now. But so having this, so this is here, is this section here, okay? This first one in here is really a dielectric loaded or filled, dielectric filled waveguide, okay? So we've got a substrate integrated waveguide, we've got a dielectric filled waveguide, and then we've got three sections in here of air-filled waveguides, okay? And the thing about these is that the height of these varies and gradually changes until you get to the standard waveguide that is for the rest of your system. Okay, let's get back. So so we have again the sections that we have in here is four sections. We have a substrate integrated waveguide. We've got a dielectric filled waveguide, which is just a small section of a chip transformer that is basically has a tapered section of the substrate material, the dielectric material. And then we have three sections in here. We have these ones. So all these three in here are the transformer that matches the substrate integrated waveguide to the standard waveguide. That's what it is. Usually, the standard waveguide has an impedance of, say, 260 in this case. I think it's 260 some ohms. And then the substrate integrated, the substrate integrated waveguide has an impedance somewhere in the 23 ohms, okay, depending on the width that we have here, okay? So we need to match 20 ohm to 260 ohm, and we do this in the middle, okay? And that's what we're gonna present a little bit, but it's all it is simple, basically, and it's a matter like in ESOF, ADS, and other packages, AWR, and Genesis and System View. We have a multi-section quarter wavelength design calculator in there. So you can calculate, you can give it just basically the impedance in here and the impedance in here, and it does the matching for you. All right, so why do we want to do this? Why is this transition is unique? First thing is that it has, the assembly is compact because the waveguide comes in and then the feed goes out in the same axis. So there is no perpendicular sticking out pieces, okay? The other thing is that since the field propagation direction is in the waveguide is the same as the planar transmission line, okay? That has some benefits to it, okay? as far as design difficulty and so on. Then of course, we've got a matching elements between the dielectric field waveguide, DFWG, and the rectangular waveguide, okay? Can be based on ridge waveguide sections, okay? It's low cost, okay? It's much lower cost than, say, for instance, because all this is a printed PCB that you get fab. There's no components to assemble on it. There's no soldering, and there's a waveguide assembly. So you just plug it in, or sometimes they put an epoxy or some kind of sticky material in there, and you just plug it in. That's it. There is no soldering. There's no screws. There's nothing. Okay. So it's low cost in that sense. There's no soldering. It avoids long assembly times, okay, and repeatability. Of course, having no parts to screw and no soldering, you get the benefits of repeatability and performance, okay? Now, so why SIW? So why not microstrip or strip line? Because we have those transitions and we've covered those. In fact, the next video talks about a microstrip line to rectangular waveguide in line transition. I've already done it. I was going to present it in this session, but it would have been too much, two of them in one video. So I split them up. So SIW first, it has a low loss transmission compared to microstrip lines, okay? And especially at KU, KE bands, okay? And you can refer to books on that and look it up, and you can see why. It can handle high power because it's really a waveguide. It's a TE10 propagation mode waveguide, okay? So unlike microstrip, which has limitations on that. It is suitable for integration. Of course, same as microstrip line. It is suitable for integration as well, because if you have a low noise amplifier, you can directly, it would be the same card that comes in and has the SIW into the waveguide assembly. That one has the LNA or the power amplifier assembled on it as well. Suitable, it's easy to fabricate. I think we mentioned that already. So let's look at this again, review this, okay? So we've got the substrate integrated waveguide in here. We've got a dielectric field waveguide section in here. And then we've got the multi-stage, multi-section lambda G/4 Chebyshev impedance transformers. I also want to point out that there are so many MATLAB codes, people that did multi-section quarter wavelength Chebyshev or binomials or Bessel or some other form. They're exactly like filters. They have, and I will show you in a minute, Bozar book, chapter 5, basically presents all these theory, and they have good examples in there. So there are MATLAB code. You can go to mathworks.com and you can look that code. There's a lot of code. Just type in there a multi-section quarter wavelength Chebyshev impedance transformer, okay? And you will get MATLAB. There's also Excel sheets, calculators that have people done. Like Microwave 101 did that. They have one on their site, and I downloaded it, and I'm going to use it in a minute just to illustrate that. So the first part is the substrate integrated waveguide transmission line or waveguide, whatever you want to call it. The second part is the transition from the substrate integrated waveguide to the dielectric field rectangular waveguide, okay? The third part is the transition from the dielectric field rectangular waveguide to the standard air-filled rectangular waveguide, which is this section in here, okay? The fourth part is the multi-section, in this case, this one here, lambda G/4 Chebyshev impedance transformer implemented as a stepping, okay, in the waveguide heights, okay, that's this guy here. All right, so the fifth part is the, oops, that's a typo, sorry about that, the air-filled waveguide, which is a standard waveguide here. Now, So just to make a remark here, which is important, we know that the height of the dielectric field waveguide is equal to the substrate height, okay, or thickness. But the width, so the width of this is exactly the same width as the waveguide. So as far as you can see here, this waveguide and this waveguide, they exactly have the same cutoff frequency, supposedly, even though they have different heights. The height is basically has impedance only. TE10 mode propagation is related to the width, which is the A width here. That's a broad width of the waveguide. Therefore, the reduction in the reduced air or dielectric field rectangular waveguide height A does not affect the propagation of the TE10 mode inside the waveguide or inside the stepped ridge transformer. Okay. Now, this here shows an example. Of course, why would we have 3 in here? I just happened to pick 3 for myself because that was based on the fact that many of the publications that I've looked at used 3. They said 3 is sufficient a lot of times for practical bandwidths of signals like 5G signals and SATCOM signals for the bandwidth that they have. So, but this is an example that shows you the impact of basically the multi-section quarter wavelength transformer. This is an example from Beaux-Arts, chapter 5, okay? And so it shows how you transform 10 ohm to 50 ohm, okay? So now the multi-section quarter wavelength is basically always, we are trying to match a real impedance to a real impedance. And usually it's a small impedance to a standard impedance, like 50 ohm, or large impedances as well. So, but usually the ratio is a little bit large, okay? So the width of this really determines the bandwidth, okay? So there are some calculators that Beaux-Arts showed, the calculations where you can determine how much bandwidth you want. And that's the first thing you want to feed into these equations is the required bandwidth, how much, maximum return loss, how much, okay? And then start plugging numbers and you end up with a table of impedance values like these. Of course, now these numbers in here, as you can see, even though he drew them as a strip line, where a macro strip line, where, for instance, as you go higher and higher toward the load, the impedance gets larger and larger, and you can see that it gets narrower and narrower, okay? Exactly the same thing with the waveguide, okay? So the waveguide in here, you know that the height is proportional to the impedance. So meaning that if this aperture, if this standard waveguide section here has 260 ohms, you can see that this one is almost like 70% of that, maybe 200 ohms. If this is like 260, this would be like 170 or so. And this would be like 120. And this would be like 70 maybe, okay? So, and that's what you end up with a lot of times. So you could implement this transformer and the one that Beaux-Arts showed, and some of the ones that you can use the calculators to come up with these impedances. These impedances now, of course, the length is equal. It's quarter wavelength. That's the starting point, but it's the actual final designed optimized lengths are not the quarter wavelength. They deviate a little bit because we really don't have a source and a load that is pure real. We always have susceptances. And of course, also the steps, the sudden change in impedance in here, that's capacitive parasitics, okay, that we don't account for in this calculation of these impedances. So that's why when you put this in, you get a nice plot like this, okay, with minimal ripple. But as soon as you implement it with that same impedances, be it waveguide or be it a ridge, a metal ridge to a coaxial inline transition like I did in the last video, you still have, it doesn't come up exactly optimized. You have to, and that's where the beauty of and the need for 3D modeling using HFSS or some other package, CST or whatever, okay? Where you put it in and you parameterize it and you run optometry in it and you can get it optimized, okay? Now, last time, whoops. Okay. Last time we did this transition. This was a coaxial inline, coaxial to waveguide transition. And in there, we took the inner connector, as you can see, it went in and it has a ridge that transformed the impedance from coaxial impedance, 50 ohm, to the impedance of the waveguide, which was somewhere between 200 and 300 ohms, if you recall. Now, what we're doing now is a little bit different, but it's the same principle, okay? So we have a waveguide. The way we start designing this is we have a waveguide in here that you pick as your standard waveguide to implement your system, or you're given that most likely. So the first thing is you want to find the impedance of that waveguide, okay? So you take the ratio of B over A, okay? And then B over A, and then in that case, you can get that number in here. And then, of course, you have the impedance of substrate integrated waveguide. There are equations to do that, okay? And then what you need to do is from here to here, come up with a series of transition of stepping in heights until you get from the SIW impedance to the the waveguide impedance, which is calculated in here. And the stepping here, the heights, really follows this equation in here. Because as you can see, if you want to find the impedance, you have to find what B is. So we get B and sub N. N is the section. So this is section 1, 2, 3. And you can calculate this. Of course, you use the waveguide, whether it's air-filled or like the first one is not air-filled. So you use, in this case, it's a duroid. So you use 2.2 in this case. Where the other ones are, they have basically the square root of epsilon r is 1, because you have air-filled, okay? And that's really the principle. It's pretty simple. So in your case, you would go in and you would put in your impedance in here, your impedance in here, and there comes 3 different impedances. Those 3 different impedances, you bring them in here, okay? And you can find what the height has to be in every one of them. Now, it just happens that the first one, we have to choose the height as being the substrate height. The SIW substrate height is exactly the same height as the first one, or the height in here is equal to the thickness of the substrate plus the copper on top and bottom, okay? So it's very straightforward. So again, what I did is I got a few things that can help you do that design and understand that theory. The first one is chapter 5 in Beaux-Arts book, okay? And Beaux-Arts book, if you don't have to go out and buy it. There's so many people, I don't know, it's out of print maybe and doesn't have a copyright, but unfortunately to them, there's many places they have the book in PDF, so I don't know. The book might be that one of the editions might be, as you can see here, it's the 4th edition. This is a very popular book. They are way out now, 6th or 5th. I forgot how many they went. The other one is this site here, and I will put it in the video down here in the notes. You can go to the notes. I'll put this link in there so you don't have to try to type it. This here has from one of the universities, I think it's Kentucky University, maybe in the US. Oh no, ITTC. Oh, that must be Indian Technologies. Whatever that place is. But this gentleman here, he teaches a course on microwave, and he put a nice section on chip-to-chip multi-section matching transformers, okay? Now, there is also this website that I found that frequently pops up when you mention multi-section matching transformers, okay? This gentleman here has a bunch of videos that shows, in fact, his videos is exactly this book. I mean, it seems like he has a course where he went in. He has a little accent, heavy accent, but you can manage. So he has a lecture that he goes through this book complete, and it's a tremendous work. Okay, so the prior to that, the way you come up with the number of sections and so forth is based on these equations, and these are from Bose basically. I mean, or it's based on, they're in Bose book. Okay, so one of them is we have to find this value here. That is basically how much is the maximum attenuation. Okay, and it's inversely proportional to the Tn, which is the Chebyshev polynomial, and a value which is called phi m here. And phi m in here, it's based on the bandwidth. Okay, so you take your bandwidth over twice the center frequency, and you get that number in here, and you put that number in here, and this is known, of course, and then somehow you come up with this with these numbers. Okay. Now let's go to and like I said, many people did this calculators, you know. So here's one calculator, this one here, and this one here. You can do maximal flat. You can do equal ripple. Now equal ripple is basically Chebyshev, and you can do exponential. And there's even one that has a Klopstein, the Tabor Klopstein transformer. So you can see here, for instance, if you have a, let's see, the input impedance is 50 ohm, and then well, let's do the one in our case, which is, we've got 20 ohm or so. And this one is the waveguide is 267. And of course, we don't want to go 8th order, but if we go 3rd order, okay, so we got these impedances. So you got 54, 73, 97, okay? And he gives you a little calculations in here of basically the impedance ratio, fractional bandwidth, 16%, the worst case return loss. Oops, that doesn't make sense here. Oh, because of the frequency. Anyway, so you can use this, and you know, if you don't like to use that one, there are some MATLAB code that you can use. Okay. All right, so let's get back to here. I apologize for this. This is not PowerPoint, so oops, what are we doing? Oh, I clicked on that link. Okay, so all right, so let's get back to this. So again, let's go to the design. The first thing I did on here is I designed the substrate integrated waveguide. So once you do that, you have the substrate integrated waveguide section. The length of this doesn't matter because this is just a piece. So you can grab, say, 1/2 inch or 1 inch. And the material is Duroid 5880. And this is what I got. Okay, the cutoff frequency is 15 gigahertz or so. And it's pretty good. Now, you can see that there is tiny slight difference between the S21 and S12. And that's because one of the vias in here, I took it out on the side of the transition because it was hitting the metal for the waveguide assembly. So I took this out. So there's a slight little bit of difference, but it's negligible. Okay, so you can see that the impedances on both sides, one is 28 ohm, one is 22 ohm, just because of that via. Okay. The E field propagation, you can see it's not leaking, so it's pretty good. All right, so, and then I go in and figure out how much I want the length of this Hilbert section, and you sweep that and you get the impedances as well. And then you start with the first transformer, or the second one. This is the second one. First one is the direct field one, and you do the same. It's 100 ohm. And then, of course, to the last one, which is in this case 254 ohms, okay? And then finally, it's to the waveguide. Oh, it's 360, not 260. I apologize. I said 260. Okay, so you can see the impedance of the waveguide, and you're sure that the waveguide is fine. And again, you start building piece by piece. So you go back and put the dielectric field with the first section with the tapered, this one, and we see that it's working fine, and the performance is good. Okay, and then we go to the next step, which is the dielectric field with the 3 sections, without the waveguide and without the SIW. Okay, and we verify that it works. Okay, good return loss and impedance-wise. And then finally, we put in the waveguide in here, and then we get this response, okay? We are sure now it's fine. And then finally, we put it all together, and that's what we get. We verify the E field is fine. There's no leakage anywhere or anything that is. So you can see in here that we've got from 22 ohm to 360. That's the impedance on the SIW, and then the 360. Now, of course, somebody might come in and say, why didn't you start with 50 ohm? Well, it just happens to be that we start the SIW, you don't want to design for 50 ohm. We usually somewhere feeding some kind of LNA or power amplifier. So that's not a problem because we can we can change that design. So it's not exactly 50 ohm. If you want to go to 50 ohm, then you have to transition from a substrate integrated waveguide to a 50 ohm. And I think we did that on the, there's one of the videos that I did on substrate integrated waveguide filters. And in there, we did that. We went through that. So you can refer back to that video. So this is the final transition performance. As you can see, it's pretty nice. And the loss is, worst case is like 0.2 of a dB, 2.5. And then the return loss, of course, is this. Now, this is pretty good considering that's a board. It's not it's not a waveguide assembly. So, all right. So this is basically, so let's go to HFSS and just show this. So we've got this. This is the, so we feed it on one side, we feed it with the wave in here on the substrate integrated waveguide. And then on the other side, we feed it with this wave in here. And then we run it. Okay, and then this is, of course, the performance, okay? The impedance on both sides is basically this. So we got 25 ohms, 360 ohm, the waveguide, of course, this one here is 360 at 25 gigahertz and 22.4, okay? And then if you want to see the E field, how it works, basically, let's see at 25 gigahertz, this is what we've got. So let me animate this. So you can see how the substrate integrated waveguide, the wave comes in and starts radiating into the substrate. And this is the critical area that you can see here. That's where the E field gets into the dielectric field waveguide section in here, where the height of that waveguide is exactly the substrate thickness. And you can see that it gets loaded like a little dam right here. It's contained within the substrate. And then the signal will start gradually building up to the impedance of 300 and some ohms that we just showed, which is a standard waveguide. Okay. Now, you can, you know, the way this design, of course, you start out with all of these parameters, okay? and they are parameterized. And so what I did is I didn't run optimizer. I just kind of went into my senses. I did the calculations, figured out the initial starting point, the quarter wavelength inside these waveguides, the one for the director field and the air field. So you put those and you figure out the height to give you the impedance. And I came in here, and you can go to any of these and start optimizing or sweeping, and then pick one of the curves that one by one. But you can really run optimizer. You can go in and come in. What would be? Let's get rid of the E field first. So let's see how do we approach optimizing this. First of all, we have the length of the SIW doesn't matter. The length of the waveguide, the standard waveguide, doesn't matter. Okay, this one here. What you have basically is a transformer, these three stages of transformer. So you have the length of the this section, the length of the section, the length of the section, the height of all of these sections. So that's 3 here and 3 here. That's 6 parameters. And then you have the length, which is really the length of this. That determines the length of the, because this here, the electric has to hit the first tip in here. That's part of the design, because that's how you can make sure that this thing goes in. When this hits this, that's part of the assembly, how you get it tied, fixed in there. And if you have some kind of glue that basically locks this in, okay. So this is part of it. So the length of this determines really the length of that. So let's pick, for instance, as an endpoint. Let's say one of those sections. Let's say that this middle section in here, okay. This one in here. If you can see that let's see the Y size is L2. Okay, so what I'm going to do is try to see now, tweak L2, so I can come in here, go to L2. This one here, and then you can put this as tunable. You can sweep it, so you can like this. And then we come into the optometry section in here, and then what we're gonna do, okay, so I'm gonna add, so we got L2 in here. We're gonna start from 2 to 6 millimeters. I'm gonna put by 0.2, or let's say 0.5 millimeters. Okay, so that just we can run it faster. Okay, so if you look at the table, that's these iterations. Okay, then we can go that, and then of course you can come into here and just basically run that. So we're gonna run that, analyze. Okay, so and we're gonna come in here, and let's start fresh. These ones in here. Let's have all of. Okay, so it's going to take some time. So okay, here we go. So it's going to start doing work, and very soon you're going to start getting, like, it started at 2 millimeters, as you can see here. Let me go and let me get rid of this and this, so we can have it. So now we can go back and put the markers. Let's see the markers at this one and this one, this one and this one. So right now, as you can see, it's sweeping basically at 2 millimeters. Where is the marker? Oh, here it is. Okay. Now it's going to put the, let me, while we're waiting for this, let me, why is it doing that? Okay. All right. Okay, well, I thank you very much for, okay, let's see. It's gonna take some time, but you can see that what it's doing, basically. You're gonna get a bunch of curves and you pick the one that you want. You can also, instead of doing that, you can actually go in, okay, here's the second one. You can see that, the second one. You can come in, which is better, and then do an optimization actually. And the optimization, you pick the parameters that you want to do, and then you basically add some instructions how you want to optimize. You want your channel loss, say between this frequency and this frequency, that much, insertion loss, this much and this much, and then goes in and it runs and does that. So okay, so this is it. Thank you very much and have a great day.